So here we've got this question on the intermediate value theorem. So there's three conditions that have to be met before you can use the intermediate value theorem. So you have to, when you're verifying, you have to state that you have met all three of those conditions. So the first one is that f is continuous, and we know that because why? Because it's a polynomial. Second condition is that, what must be true? You have a closed interval. And you can see that because of the bracket. So you can just say -5, -2 is a closed interval. And the third condition is what? Now this 5 has to be in between f of a and f of b, which means you got to figure out what is f of a and f of b. So f of -5 is going to be -5 squared plus 3 times -5 plus 1. I guess that's 25 minus 15 plus 1, so that's going to be 11. Does that sound right? And f of -2 is going to be -2 squared plus 3 times -2 plus 1, and that's going to be 4 minus 6 plus 1. We try -1. Is that okay? And so our 5 is going to be in between. Let's see, the smaller one was the f of -2, and the bigger one was the f of -5. So now we have met the three criteria for the intermediate value theorem. So now that means the intermediate value theorem applies. And the intermediate value theorem says the function must be equal to 5 for at least one value of x on that interval. So now we're going to take the x squared plus 3x plus 1 equals 5 and try to solve that. So with a quadratic, we're going to make it equal to 0. And we can factor that. And that's going to factor into, I think, plus 4 minus 1. So it looks like we can get both -4 and +1. But the the 1 isn't on the interval, but the -4 is. So our value of c is going to just be -4. Okay, any questions from the homework? Would you like to see? Does that help a little, Katie, on that one? Can you give it a try? Let's see. Yeah.
Can we do 24 on homework 14?
On homework 14, do you know what that's the limit one, right?
Yeah.
I
have it.
Okay, so what do you know the number?
24.
24. And that's the limit is what?
So, or no, it's not a limit. It's a graph.
Oh, it's a big graph one?
Yeah, kind of. Well, like you have to find the right hand and left hand limits.
Okay.
So, it's x minus 2 over x minus 1 and comma, and x is greater than or equal to 1. And then x over x minus 1, comma, x is less than 1. And
So we want to find the left and right hand limit.
mm-hmm.
So the left hand limit, which is also known as the limit as x approaches 1 from the left. So that means we're going to come in from values of x to the less than 1. So as we plug in values of x that are less than 1, think like 0.9, 0.99, 0.999. The numerator is always going to be positive. The denominator, 0.9 minus 1, is going to be a very small negative number. Okay, so I'm going to try to denote that. This is kind of my own made-up notation. So I'm saying 0, but it's going to be a negative, a very, very small number, but negative. So you take a positive number that's not 0, divided by something very, very small and negative, the result is going to be and what kind of a negative? Small, big, medium?
Big.
Huge. Yeah, so it's going to be a very large negative. So it's going to go, we could say it goes to negative infinity, or we could say it doesn't exist. Either way. Kind of implies we want more information than just does not exist one. We want a left and a right hand limit. So the right hand limit, which is known more officially as x approaches 1 from the right, from the little plus, now we're coming in from this side. Now same story, as we plug in, we have this x minus 2 over x minus 1. So as you plug in a number like 1.1, 1.01, 1.001, this number on top is not going to 0, but it's going to always be negative. The number in the denominator, which is going to be a little bit bigger than 1, is going to be very, very small, but positive. So small positive. So it's going to go to negative infinity as well, which, I mean, you could get away with saying does not exist, but probably we want more than that. Is that okay? What else? Yeah,
Could you do 25 on the review, please?
25 on the review. Okay, so this is the big graphing one.
Yes, sir.
You want to ask me just a little easy one, huh? Just messing with it. So I'm going to put in the information here in green, and then we'll come back and we'll draw it in a different color. So whenever x goes to, is that infinity is -1? So if it means when you go way out to the right, it's going to approach y equals -1 as an asymptote. Going across, that limit as x goes to negative infinity is going to be +3. We're going to have a horizontal asymptote to the left of +3. The limit as x approaches 2, which way do you want to go? 2 from the left, the -2 from the left is negative infinity. So a -2 is going to be a vertical asymptote. And to the left, it's going to go to negative infinity. As you approach -2 from the right, it's going to also go to negative infinity. So it's going to go down that way also to the right. And the limit as x approaches 3 from the left is negative infinity. Another vertical asymptote equals 3, and to the left, also negative infinity. And to the right, it's going to be a positive infinity. It's going to go that way to the right. As we approach 5 from the left, it's going to be 3. So 5 wants to be 3, a little tail on the left side, because that's just coming in from the left. And as you approach 5 from the right, it's going to be 1. So from the right, it's going to be there. And down at the very end, it says f of 5 is 3. So that means this is going to get filled in. Okay? And then it says as we approach -3, it's going to be 1. And that's, they didn't give us a direction, so that's intended then to be a two-sided limit. So it's going to approach from both sides. And f of -3 is actually -1. So it's actually going to be this point down here. Okay? So now I'm going to actually put the graph together. So going to the far left is going to approach this asymptote. As we work our way left to right, the first information we get is it's going to approach this from the left. So we're going to go feeling cautious and not very ambitious at this point. I'm just going to go straight to there. That's going to leave on the other side here, but it's going to give us this solid dot. And then as we work our way here to the asymptote, we're going to dive and go down. So that's going to take off and go down. Okay? So we're going to hop over the asymptote, and it's going to be down here again. And as we work our way left, I guess it's gonna have to end up going down there. We have no information about how high up it goes, so you have artistic license to just come up a little bit, come way up, whatever you're feeling will work. Okay?
Okay.
Then we hop over the asymptote, now we're way up here. And the next thing we see is we gotta come in from the left side here. So it's gonna do something like that. But it leaves from down here, and then has to approach this. Now I'm feeling more confident, or more ambitious. I think it's gonna approach that asymptote by crossing it into a number of times. Just the feeling I get. But you can have a different feeling and do it a little differently. Okay? What else?
Can you do 11?
11. Yeah, now these are, we have to, this is one of those we kind of have to get a familiarity with, because these come up pretty regularly. And you just have to see them a few times before you start to know what to look for. So on 11, you have the limit as x approaches 8 from the right, is that right? And we have this. So if you just plug in 8, you're going to get 0 over 0, which is indeterminate. If you factor that 2 out, then this kind of a graph here, where we've seen absolute value of x over x, this is a translation of that. So what's going to happen is, and there's not a great way, I think, to like factor it. You can't factor and cancel it. But as you plug it, as you come in from the right, numbers that are bigger than 8, say 9, 10, 100, then what you get when you subtract 8 is positive. So 9 minus 8 is 1, 9 minus 8 is 1. These will be the same thing. They're going to cancel, and you'll just get 1/2. Same thing if you put in 108. 108 minus 8 is 100. Absolute value of 100 over 100 is 1, times 1/2 is 1/2. So if you were to graph it, and you don't have to, but if you were, you know, if this was 1/2, to the right, this is always the same thing. Now when you get to 8, 0 is undefined, so it's not defined there. But then when you cross over to the negatives, or something less than 8, like say 0, you know, 0 minus 8 is negative 8, the absolute value makes it positive 8. Here, 0 minus 8 is negative 8, so 8 over negative 8 is going to be negative 1 times 1/2. And so now it's going to be negative 1/2. And it's going to be that way all the way, no matter what you choose there. So this absolute value of x over x is this graph that does something like that. And then there's variations on it. You know, you can translate it by, you know, going -2 plus 5, whatever. You can stretch it or shrink it by multiplying it by a different number. But it's going to still look as a variation of this. Okay? So for us coming in from the right, this is always going to be 1/2, 1/2, 1/2, 1/2, 1/2. Doesn't matter what happens at the point 8, because this is actually at x equals 8. So the limit is going to be from the right, is going to be a positive 1/2. The limit from the left would be a negative 1/2. The limit as we approach 8 would be, does not exist. What else? Okay, so we're clear, we're testing again on Friday. Seems like we were just there. We had so much fun then, we'll do it again. Remember to bring your notes. I'm going to try to check all the notes from the last assignment since the last test there. Remember that if you haven't already, I don't know if it's even open anymore, but you're going to get a grade in this chapter on the AP classroom stuff. Getting on there twice, we had an opportunity to get on there and do those. So if you haven't, I don't know if it's even still open. You have to email me and I'll open it up if you haven't. That will close after Friday. So let's talk, we're moving on, we're going to talk about 2.1 velocity and speed. And I'm going to give you a table of values here. And then we're going to, so this is like, imagine you toss an object up in the air, and we're just measuring its height at various time intervals. So we're going to have time given in seconds, and we're going to have height given in feet. And I'm going to give you a little table that we'll refer to. So we have 0, 1, 2, 3, 4, 5, 6. Now we're going to have 6, 90, 142, I believe, and 162, or 166 rather, I think. If I could read my own writing, this would be better. Now I'll go with 162, sorry. 150, 106, and then all the way down to 30. So I want to talk about a couple of things here. First, I want to talk about tables in general, particularly with respect to the AP exam, what you can assume and what you can't assume. And then we're going to try to talk about what's the difference between velocity and speed, because that's going to come up a lot in here. That's kind of a nice source of examples. And then we're going to try to approximate the speed at t equals 1. So all those things I want to talk about here. And then we'll get away from the table and we'll do it some other ways as well. So when you see in general with a table, there'll be a body of a question. And that may or may not give you more information about how the function behaves. Is it continuous? Is it differentiable, whatever that means, or not? So they don't tell you that information. You cannot assume how this function behaves in between these known values. Now, this particular example, if we're talking about throwing an object up in the air, it's going to behave in a much more predictable way. But if it wasn't something like throwing an object up in the air, but just some random function, we have no idea what happens in between 0 and 1. You know, it looks like it's going up from 0 to 1. Certainly it is, but what does it do in between there? It could do all kinds of craziness in between there. And we can't assume that it doesn't unless they give us more information about how it behaves. Is it continuous? Is it differentiable? Is it always increasing? Is it always decreasing? Those kinds of things. You with me here? Well, you're just a liar. Okay? So don't assume because you know these points that you necessarily know what happens in between. Okay? Now, in this case, you have a little bit more because, you know, throwing an object in the air can't be very erratic. You know, it's going to be much more predictable. Okay, now, you see the largest value at 162 at t equals 3. You cannot assume that is the highest value. Because if we're just graphing this piece of it right here, you know, we know that at 2 seconds it's 142, then it's up to 162, then it's at 150. But we don't know that the curve does this and not, you know, does it, you know, hit a higher point some other place, or hit a higher place and then come down. You see what I'm saying? So just because this is the largest value we know, we cannot assume that is the largest value ever on this curve. So be careful about assumptions that you make when you have a table of values. You have to have more information before you can make those assumptions. So what we want to know is, can we approximate the speed of this object at t equals 1? But before we do that, we need to talk about the relationship between velocity and speed, because that's going to come up a lot in here. So velocity is the rate of change of position. Rate of change of position. So in particular, we are going to talk today about the average velocity, which we could have talked about last year in AP Prep, and we did a whole bunch. That's going to be an average rate of change, which we've talked about at great length, but we'll remind ourselves. The instantaneous velocity is going to be the instantaneous rate of change of position, which is a calculus topic, which we're going to also talk about a little bit later today. So velocity is going to, now velocity could be positive or it could be negative. So we will look a lot at examples of position, particles moving, position, whether it's an object thrown in the air or like, a squirrel running along a tight power line or something. But objects that will move either along the x-axis, so all they can do is go right and left, or objects going up and down, up, down. Vertical is positive, or going up is positive, going down is negative. Going right is positive, going left is negative. So velocity can have a sign with it. If we're talking about horizontal, positive velocity means the object is moving right. A negative velocity means the object is moving left. Vertically, positive means it's going up. Negative velocity means it's going down. Speed is not interested in sign. So speed is always the absolute value of the velocity. So if an object is going up at 5 feet per second, its velocity is 5 and its speed is 5. If an object is falling at negative 16 feet per second, it's going down, its velocity is a negative 16, its speed is still 16 feet per second. It doesn't care about which direction it's going. Okay. So if we're going to approximate now the speed at t equals 1, we don't know the speed at, remember this is position here. That's how high it is up in the air. We don't know, it looks like it's moving up. So it looks like anyway that the velocity is going to be positive. And the speed is always going to be positive or 0 because the speed can't be negative. So if we don't know the velocity, we only know its position, how do we approximate the speed at t equals 1? Well, there's 3 ways we can do this. We can use the positions we know, the one that we know right at time 1 and the one right before it, time 1 and the one right after it, or the 2 positions on either side, in a sense, kind of average it. Does that make sense? So one way of approximating the speed at time 1, or velocity, either going to be positive, so we don't have to worry about that, is we can do the average rate of change. We can take the position, I guess we'll give it height. Height at time 1 minus height at time 0 over time 1 minus time 0. Remember doing this before? This is like a slope, y2 minus y1 over x2 minus x1. We tried to work really hard last year about getting more comfortable with calling it, like functional rotation like we see here, h of 1 minus h of 0 over 1 minus 0. And of course, as you know, we're going to get to our favorite problem pretty soon. We're going to call that h of 1 and h of 1 plus h. And we're going to even add to that. Oh, this is going to be fun, just like old times. So we can say that one approximation to the velocity, or speed, in this case, is h of 1, which is the 90, minus the h of 0, which is the 6, and then 1 minus 0 is 1. With me here? And so that's going to be 90 minus 6, 84, is that right? And what would our units be on that?
Feet per second.
Exactly, feet per second. Very good. Feet per second. Okay? Now that's one way of approximating it. Now, second way is we could use the value at the time we're interested and the one a little bit later. So we could say h of 2 minus h of 1 over 2 minus 1. That would be a reasonable approximation to the speed or velocity. And so h of 2 is going to be good, 142, minus the h of 1, which is 90, and 2 minus 1 is 1. See, 142 minus 90, I got 52. Does that sound right? And again, feet per second. So that would be reasonable also. And a third way we could do it that would still be reasonable would be to take the point on either side of time 1 and use those, do that average velocity. So we could take h of 2 minus h of 0, and then we'd have to go 2 minus 0 in the denominator. We good to go? And so h of 2, I think we'll put 142, is that right? Minus 6 all over 2. Uh-oh, 142 minus 6, is that like 136? Divided by 2, I know we're pushing some of us here. stalling, give me time. Okay, I'm ready. Oh, you guys are good. 68 feet per second as well. Okay? Now, we're limited here. Those aren't great approximations because so much time has elapsed that this thing has really traveled a long way. So we would get a better approximation if we could change this delta t and make it smaller. You know, if I could find, you know, the time at 1 and maybe the time at 1.1 seconds or 1.01 seconds. But I can't do that with a table. So I'm going to help you out here. I'm going to give you an equation for this h of t. So either we need more data points to get a better approximation, or we need an equation. And I mean, I could easily make up more data points and make those up. So we can say h of t is 6 plus 100t minus 16t squared. So now what we're going to do is try to get a better approximation. You might want to, we're going to use our calculator. Okay? We're going to do this at a bunch of times at a different point. So you might want to enter this as y1. So this is going to be a lot more efficient and less annoying in terms of typing this in over and over again. If we just put this function in as y1. So if you want to enter that into your calculator at y1, then what we can do now, same idea that we had before, but now we could say that the speed at t equals 1 is going to be approximately equal to, and let's use, what do I want to do? Let's do h of 1.01 minus h of 1, and that'll be all over 0.01. Does that make sense what we're doing here? Katie? You okay?
Yeah.
You sleep with your eyes open remarkably well. What a talent that is. So we have point to, on your calculator, go y1, which you have just, remember how to do y1? So you have to go variables, it's right left of the clear button. Yeah, right here, I don't know what it is, I forget what it is. Help me out here. You need the calculator? Yeah. Oh, boy, you're in luck. Anybody else need a calculator? So if you go y1 of 1.1, so go variables, let's go second mode first, second mode. Then go variables right next to the clear button. Right arrow, enter, enter. And then go parentheses 1.01 and close the parentheses minus, and we can go again y1, so back to variables. We're going to be good at this. Right arrow, enter, enter, parentheses 1. And hit enter, and then divide that by 0.01. And are we getting something like 67.84? Anybody else getting that? Anybody not getting that? Now celebrate when you get that.
I'm still on the finding the variables.
Matter if it's in radian or degree mode?
No, it doesn't, because they're going to assign it closer. So variables is next to the clear button. So did you enter this y1? Clear left.
I did that.
Right arrow.
Right arrow.
Enter. Enter again. Parentheses. 1.01. Minus. Clear. In the parentheses. Okay. Minus. That's the variable. You got it. Kayla, you get that?
Yeah.
Oh, no, when you calculate.
Okay.
All right. You got it? Got it?
I do know.
You did not. You didn't say. Okay. This is good.
Okay. So I'm here. Is this where?
Oh,
yes.
Okay, now we're doing it. Oh,
Oh, you
you
need
did
that.
it.
Then,
But
yeah.
I did it right.
You
So
know,
now you
do
do,
it. Yeah, but
you
you
put
can
the
do that.
parentheses
Go
on
second
the
one.
one, yeah?
Yeah.
Now put another parentheses, and then you do the same thing, so you go to y,
And that's
variables,
Now that you have the right,
Yep, and
still using
put
Y1, but
minus
now it's the right
one.
Y1. Then divide by 0.01. This might be screwed up.
Minus, oh, you have to put a parenthesis, oh, sorry, okay.
Yeah, I think it's-
Hold on.
and I still second mode.
So, yeah, so it's one parentheses one minus one
Oh, did you
parentheses
have
one.
another-
Oh, I put an extra.
Oh, I see, okay, I get it now.
I'll go back to second mode. Okay, now go,
Oops, I keep forgetting the parentheses.
second,
Dang it.
go second and third. No, it doesn't. Okay, so now go back up. Just clear. I thought maybe you already entered it in there.
You have to divide it by
So,
three.
I was like,
try that out. Enter. Now parentheses 1.01. You know where we're going now? Okay, got it? Yeah? Well, it's okay. Want to hold that for you? Yeah, I'm happy to help. Okay, so we got to there. So now let's do it on the other side. So once we all get to here, let's do, so on the other side, we're going to go h of 1 minus h of what? Yeah, so we added 0.01 to the 1, now we're going to subtract 0.01 from the 1. 0.99, phew, that was some heavy duty arithmetic there. And so now we have 1 minus 0.99, it's still going to be 0.01. Okay, do that on your calculator. I got my answer on the board, are we agreeing? If not, we gotta figure out what we're not doing right. Okay?
Yeah.
You don't sound okay. We doing all right? Got it? Priya? Okay? Okay, so we see now, let's think a little bit, what does it look like this is getting closer to? Can you tell? Yeah, I mean, that's awful close to 68, so is that. Well, let's test that theory. Let's go 1.001 minus h. Isn't this fun? Don't answer that, it's a rhetorical question. All right, go ahead. You agree, Katie? That doesn't mean you get to take a nap. Okay. Now these are still approximations to the velocity at time 1. These are still average velocities just over a very small interval. And of course, the smaller the interval we make, the better the approximation, okay? Then we not get 67.984. So what are we going to do next? Oh, come on, you know. H of 1 minus H of 0.999. Guys, it's like you read my mind, it's scary. So it looks anyway like our observation here that the instantaneous velocity at time 1 we thought looked like it was going to be 68, and this looks like it's confirming that. Because now we're even closer, and we have a better approximation, and these are both closer to 68. Now each of these is an average velocity. So anytime you have two distinct time values, So your position at one time, so average, let me say that, average velocity from t equals A to t equals B is given by S of B, I don't know why we use S, but usually S is used for position. S of B minus S over A over B minus A. That is the average because it's over a finite time interval. Now, you will be asked at times on the homework to approximate the instantaneous velocity by using an average velocity, and you can do something like what we've done here. And the smaller you make the interval, probably anyway, the better your approximation is going to be. So, how do we find the exact value? Okay, let's back up. Another way of saying this average velocity. So we have here, we were approximating the velocity or speed, because they're the same one as positive. The velocity, I'm going to say, at t equals 1. And so we did, because we had h of 1 minus h of 1 plus h, where we chose different values of h, right? We chose the very first one off the table. What was the h? How far away from 1 did we go? Very first one off the table. 1, yeah, the delta time, the change was 1 over that h. So that's that's an approximation. Then we used h to be 0.01 and then 0.001. So if we want to make it exact, what do we want to do with that h? We are going to, okay, speak to me in math language. We want to make that h get smaller and smaller. We want that h to get closer and closer to, this h has to get closer and closer to, how do you say you want the h to get closer and closer to 0? You say this h goes to 0. Come on, calculus students, right? Of course it is. We know how to do that. We did this kind of stuff all the time last year. Now we're just going to add the limit on to it. Oh, I don't think so. Okay, let's see if we can do this. Oh, this is fun. We're going to do some calculus. You ready for this? Can I answer that? So we're going to take the limit as h goes to 0 of h of 1 plus h minus h of 1 all over h. Oh, it's like being re-traumatized, isn't it? It's like you're afraid to go to sleep at night, the nightmare is going to come back again. It is. Here we go. Okay, I'm going to plug in 1 plus h into here. You ready? I'm ready to write. Tell me what to write. Good. Just me and you, I think, Ainsley.
Times 1 plus h minus 16 times 1 plus h squared.
Is that okay? There's some whimpering there. Just need time? Okay, now minus. Somebody help Ainsley out. I think she's carried you guys for long enough.
6 plus 100.
Times 1.
Yeah, minus 16.
Times 1 squared. All over. You okay? We've done this before. We know that everything that doesn't have an h in it better cancel. Okay, so we have limit. H goes to 0. See, we got 6. We'll distribute that plus 100 plus 100h minus 16. Oh, I need a little help here. Now we're going to square out 1 plus h. Remember we did this all the time. It's a shortcut. First one squared, twice the product, plus the second one squared. Good.
2h.
Nice.
H squared.
Oh, you're a champ. Okay, and then let's see, 6 plus 100 is 106. Then you go 6 plus negative 16 is negative 10. Negative 10 plus 100 is
90.
oh boy, that was slow. Okay? All right. A good feeling about this. Okay, so here we go again. 6, 100, negative 16. That's going to be 90, yes. That's going to cancel with that negative 90. Oh, not that 16. Hold on, that will carry away. How about, oh, what did I do there? Oh, because I had to distribute that. I'm ahead of the game. I did, that 16 is gone. I did. So now I'm going to confuse you. Now P is whimpering is going to get pronounced. So the negative 16 I cancel. We still got negative 16 times 2h. Lose you? I did? Okay. And then we're going to get, okay, still all over h.
Wait,
Yeah.
what? Okay, go back to canceling. What?
Yeah, I did. Okay. All right, let me do that first. So I'm going to say, I did get all the 6 plus 100 plus 100h. Now I'm going to distribute. Minus 16, minus 32h.
Okay.
Minus 16h squared. That was my fault. I was just so excited to get a chance to cancel. I kind of jumped the gun a little bit. Take a few deep breaths. Let me calm myself here. Okay. 1600 negative 16 is going to be positive 90, minus 90. These are going to all kill each other out. And then we can say 100h minus 32h is going to be 68h. Minus 16h squared, does that look good? Still all over h. What next? Factor that h out. You get to cancel the h. Now, AP prep students are done. Calculus students step to the front. They say the limit as h goes to 0 of this is, because you direct substitute in the 0, it's 68, like we thought. Okay? We found a derivative. That is h prime, the derivative, evaluated at 1, is 68. That is our instantaneous rate of change. Our velocity is 68 feet per second at t equals 1.
Wait, 100 or negative 16h?
Because h goes to 0, so
Oh, I
you
see.
direct substitute that in,
Okay.
and it goes away. So all this stuff we did last year in AP Prep was so that when we get to here, all we have to worry about is the calculus, that limit stuff. Because this other stuff is all new.
It was just writing and not really processing.
Uh-oh. You have to relook at that. So we can do one quick. You got your calculators handy still, right? You didn't pack that up yet, Katie?
No.
You sure? You gonna dig it back out? So can you estimate the limit as h? This is the kind of question you'll see on your homework tonight. So it seems like it's not telling you enough information. The limit as h goes to 0 of 5 to the h minus 1 all over h using your calculator. So we're estimating it, so we're not trying to do what we just did there with the whole limit as h goes to 0. And you can use your calculator. They do not give you any kind of direction about what to choose for h, so you have some freedom. And so your answer might be a little different than your neighbor's answer, might not be exactly what the answer is in the back of the book, but that's okay, because If they want you to get exactly the right answer, they'll tell you what to use for H. Just so we can do the same thing, what do you want to use for H? Cannot use 0. 1. I'm gonna pretend I didn't hear whoever offered up 1.
2.
No, it's gotta be small, it's gotta be close to 0. You can use a calculator. What's that? I think I heard somebody say 0.01. Thank you. That's a reasonable effort. Okay, grab your calculator. 5 to the 0.01 minus 1 over 0.01. Come on, Katie McPherson. Turn on your calculator, turn on your brain. And we'll see what we get. No, I used a different one, so you tell me what you get.
Did you get 4.07?
Say it again.
4.07.
Anybody else get that? Did you divide by the 0.01?
Yeah.
That sounds good. Need to be decimal places. 1.6, 22.
Oh, damn.
Priya, you figuring that out? I was gonna have you do one exactly, but you're saved by the bell. I can't believe it. Questions for the greater good? Maybe 12, is that working for you?